this atomic inner shell laser. And it's an amazing thing because all it is like a gas cell full of neon. And it was, let's see, with about 500 torr, a couple centimeters long. And you shine the XFEL into this gas cell. And it creates that population inversion all along the gas cell. The spontaneous emission that's emitted at the front gets amplified as it goes all the way through. You disperse the radiation onto a CCD detector, and you can watch and you can see what actually happens with those two things. And it's quite remarkable, right? So here's where she came in with the XFEL pump, and here is the actual neon X-ray laser, which is exactly that same line that we were using for the Rabi flopping earlier. It's just this 1s to 2p line, the Lyman alpha line. It's very, very stable with respect to the pump laser, and it has the same divergence as this pump laser. And so if you go and take a look at what happens as a function of the incoming power, what you can see is that the flux in the X-ray laser has increased by 10,000 times for just a twofold increase in the pump power. So you've really, you can really see this exponential gain. And so that's very, very, I would say, impressive. So later on, yes, she and her student, Clemens Wenninger, actually calculated, what did you actually measure in this? You actually measured the pulse energy and the bandwidth, but you couldn't really measure the bandwidth because that was limited by your apparatus. So you actually have to get that from simulation. And so she simulated later what would be happening as a function of propagation distance for these pulses. And in this gain regime, then you could actually show that you could have some transformer pulses here, but that the spectral bandwidth was kind of high-ish. First it went down in this narrowing region, and then went higher after propagated, and the pulse duration had this unusual shape associated with it. Okay. There's also exactly the same thing done for copper. Okay, and this was done at the Japanese XFEL, where they have maybe not quite as much pulse energy, but they basically took it and focused their 40 microjoules, which is somewhat less than you get at the LCLS, and they focused it down to about 120 nanometers onto this copper target. And again, they dispersed the radiation from it. And they saw that they could have gain as a function of the incoming pulse power. But they did one other thing that was sort of special. They have, at the Japanese XFEL, they actually have tunable undulators. So at the LCLS, the undulators are fixed gap. But at SACLA, you could actually change the photon energy coming out. So you have two pulses of different energies. So here, you're pumping above the edge so you can create those inner shell holes. And here, you can pump above the edge to create the inner shell holes, but you can also create a seed pulse coming out from another part of the undulating regime. And then you can do the same thing on your copper target and actually get out a higher intensity than you did. So you actually have seeded radiation from this. And so you could choose whether you want a K alpha or K alpha 1 or K alpha 2 seed. And as you can see, the line width for the seeded pulses was significantly more than the ASD, less than the ASD. So that was kind of nice. Okay. Now, can you still use these SASE pulses for something other than making these atomic inner shell lasers? Can you actually do these stimulated Raman processes? First, we were looking at, Rabi flopping type things. But Nina thought, oh, well, maybe we can actually do these stimulated X-ray Raman scattering also. So instead of going back to the original state, we go to some other state. And this is something that's really interesting for a wide community because it's a way for them to look at low energy excitations in, bulk materials, buried interfaces, and so on and so on. So it would be very interesting if this was working. And using exactly the same configuration, what you can do, right, is your SASE pulse covers all kinds of messy things, but you can look for stimulated emission back to this particular state, which has a 2p hole rather than a 1s hole. And again, you start with your focused FEL beam, and you can calculate some parameters for which this will work, and you can look for the amplified Raman scatter output at the end of this pulse. So does this concept work, right? So, like I said, it's basically the same apparatus as before, but now instead of tuning way above the edge to create 1s holes in population inversion, you're close to the edge and you're looking at the scattered radiation from that. So this is how that actually works. So here on the bottom, what you have is the photon energy of the transmitted radiation. And so you're scanning the XFEL up on this axis. And so when you're scanning along, here is the threshold for ionization. Here is that 1s3p resonance that I talked about. And then down here, when you're below the edge, you have lots of transmitted power because there's no absorption. And once you get above the edge, you have this K alpha fluorescence because you've made a 1s hole. Right? But near this region, near the edge, is where it's sort of an interesting process. So this is the region that gets looked at. So what you can see up here is that in this region between 846 and 852, you can see that the pulses are varying in their width and are much broader than this red pulse that comes at higher energy. Okay, so as I said, people are really the wider community is interested in this because what you can see is when you're doing this inelastic scattering, what you have is that you have, when you're below this edge, when you have a resonance, there's a dispersion of omega in with omega out because the final state energy is always the same. So you change omega in, omega out changes linearly. And the hole that you create in this process with these two photons, which you think of in a single step, is this 2p hole. So then also the line width is not broad as the 1s hole. So people think, oh, well, I can really do some better spectroscopy this way. But now, instead of coming with a nice tunable beam, well monochromatized and tunable, you have this SASE beam. So what happens is you have this resonance that you're going through. You hit a resonance and then it goes down, and that dominates, but there's some detuning. And so it's dominated by each of these spikes. So what you expect is when you're hitting some of these resonances, that actually the omega outline is going to jitter around because you're not always exactly properly on resonance. And so that is the evidence that you're looking for that you've actually caused these processes. So once again, here is 870 is the ionization continuum, and all these things down below are evidence of this stochastic scatter, stochastic line position and width moving. And so that is kind of that is the evidence that you can actually cause these processes to happen. So you can see it's just like for the Rabi flopping, it's a little bit tenuous, right? Now she went further on. This is kind of cool. Is that she says, oh well, actually this looks bad, but maybe what you can do is actually get some high resolution information out of this. if you form this quantity, this covariance, where you take the intensity of omega-1, which is incoming, and omega-2, which is outgoing, minus, the average of those two. And then you can come back and extract, these lines for all these different resonances. This is only theory, right? So there hasn't been any proof that this actually happens. Okay, so I quit now. I just summarized. It's late, tired. So XFELs operating with SAS impulses can produce these demonstration experiments, right? And so you're getting there, but we have some evidence for the Rabi floppy, some evidence for the simulated X-ray Raman, but they're really good for creating some of these inner shell atomic lasers. Clearly the neon one works really well, but it hasn't actually been used for experiments later. And these XFEL improvements, for the next level are becoming available. There are these seeded XFELs using HG film, mentioned this. This I would have to say is very cool, because not only do you get this one actually starts with a laser seed at like 260 nanometers or so and builds it up. And you can get out to about 4 nanometers, which is the carbon edge, and you actually get two, I think I may have a slide on this, maybe I'll show this to you. You actually get 2 wavelengths coming out. The seed divided by 1 harmonic, and the seed divided by, a couple of harmonics. And these two things are like phased really well together. And it's quite amazing. They have all the different polarizations that you can want. And, they operate over quite interesting wavelengths. So I would have to say this is actually quite an interesting source for atomic physics. And let's see. Right, there were seeded XFELs, both in the soft and the hard X-ray range. I told you about those. There are also 2-color FELs, those at LCLS and SACRA. So there are a lot of toys that people can play with. It's a little bit time limited for you to get time, but I would have to say that, I would say there's a bright future, in this area. There are lots of new toys that are actually just becoming available. And so with that, I just want to close and remind you, because we have a really nice group at Argonne that does AMO. I didn't really talk so much about what we were doing at the APS, because it's much more chemical dynamics on a much sort of longer time scale. But I want to remind you, we're right outside Chicago, and the things that we're doing there are really fun as well. And so I encourage you to visit the next time you're out there. And I have to acknowledge, I got a lot of these slides from Nina Warringer. Nina is a new mother, So anyway, I thank you for your attention. I know everyone's tired, including me. Thank you.
So Hassan had to go take a phone call, so he apologizes. But I'll take the questions then. Who has questions, comments? Yeah.
So is there any hope of using a synchrotron beam as a pump for an inner shell laser?
No, I really don't. I don't think so. There's not enough. The intensity that's in a synchrotron beam is down by like 9 orders of magnitude relative to that in an FEL. And so I think that would be a very tricky process. It would be hard.
There was another. Yeah.
In this Nina this inertial isolation,
Yeah.
she includes 2 parts. One is for the laser force. One is forward propagating force, and another is backward propagating force in this rectification. And I mean, in the experiment, is it possible to say this backward propagating laser?
I don't, well, not the way the experiment was done. So, I should say maybe a couple words about this experiment a little bit. So this experiment, right, it only has right? I mean, if you want to look for backward propagating, you'd have to go back out toward the XFEL, and that would be pretty difficult. So, you know, there's a little gas cell inside, you know, a chamber, and it has plastic windows, and basically the XFEL drills holes through the plastic windows, and then you just look at this forward scattered radiation, disperse it on a grating and onto a 2D detector, and then you can see, you know, the different energies that have been produced that way. So I don't think you wouldn't be able to see that, but, you know, basically everything's going in the forward direction. Because that's where your pump is going. Right? So the gain is all forward and traveling at the speed of light, more or less, through the medium.
It's called a swept gain amplifier.
Which Pierre
Worked
worked on 40 years ago. And now you can see it with the X-ray.
Yeah, it's memory lane. You know,
It is memory. Yeah, and it's X-ray. We do it for the X-ray range.
More questions or comments? I think everybody is a little bit tired, but oh, you're leaving early in the morning, right? Is that right?
No, actually, I'm leaving on the Monday.
Okay, so you have all day tomorrow to ask her more questions.
Yeah, but everyone's tired.
Yeah, but tomorrow they will be here.
Okay.
Thank you so much. It's really a trip from memory lane. It's something interesting. Because nothing standing up
Is that right?
Oh yeah, she's posted actually very early on. She well, the first seat is because we would see there's a very shiny which is I think the common stuff that she's done is kind of interesting.
So here,
Discouraged is that the big emphasis is jet.
if you find the right system, you can really do some cool stuff. I just have to figure out what it is. And then, don't you think? Let's collaborate.
So what is which one is
This is the one
Well, if you want to go to university, if you want to go downtown, there's the street park. Yeah. Public transportation.
What is it? It's near the street.
All I can say is On the hairy edge.
Ah, okay, I get it. Okay, that makes sense.
Oh, I see.
Very good to know.
Oh.
Yeah, so
They're about
so
5.
for each one,
If you know how to turn off this machine, turn it
That's the pattern.
to turn it off.